Welcome back, chemistry students. I'm Mr. Silverstein. We've been working this week on our unit on nuclear chemistry. We've already talked about the different types of radiation, why elements decay, and how they become stable over time. Today we're going to be looking at half-lives and how long it takes for that element to become stable. So I'm going to share my screen and we're going to get started. This is a fairly long session, so you may want to break it up into two seatings for yourself. But the concept here is that, and the big idea is that the half-life of a radioactive isotope refers to the amount of time required for half of the quantity of a radioactive isotope to decay. And our objective is for you to be able to calculate the half-life for a given radioisotope and calculate how much of that radioisotope remains after a given amount of time. There's going to be some reading in here, some notes, some calculating, and a recap on quizzes. Remember 7 tips for a successful study: spiral notebook for your notes, pens and highlighters, periodic table of elements, watch the video lesson, pause as you need, then go back and use the slides in present mode to refine your notes. If you have any questions along the way, email me and we'll respond to you quickly. Make sure you complete the assignment in the next tab. And remember, please, only turn in completed work. So let's review nuclear stability from our earlier lesson. Nuclear stability is a concept that helps to identify the stability of an isotope. To identify the stability of an isotope, it is needed to find the ratio of neutrons to protons. There are close to 2,000 different nuclei that are known. Approximately 260 are stable and do not decay with time. And the stability of an isotope depends upon the ratio of those neutrons to protons. And you determine that ratio by dividing the number of neutrons by the number of protons. Let's talk about nuclear half-life. And you have all this text. I'm going to read it to you so you can hear it both audio, visual, and then you can read it on your own. A half-life is the time taken for something to have its quantity. The term is most often used in the context of radioactive decay, which occurs when unstable atomic particles lose energy. 29 elements are known to be capable of undergoing this process. Radioactive decay is random, and measured half-lives are based on the most probable rate. We know that a nucleus will decay at some point, we just cannot predict when. It can be anywhere between instantaneous and the total age of the universe. And although scientists have determined half-lives for different elements, the exact rate is really completely random. Half-lives of elements vary tremendously. For example, carbon takes millions of years to decay, and that's why it's stable enough to be a component of living organisms. Different isotopes of the same element can also have different half-lives. 3 main types of nuclear decay that we learned about are alpha, beta, and gamma. Alpha decay is when a nucleus splits into 2 parts, a helium nucleus and the remainder of the original nucleus. A beta decay is when a neutron in the nucleus of an element changes to a proton. And if a nucleus emits radiation without experiencing change in its composition, it's subject to gamma decay, and gamma radiation contains an enormous amount of energy. Now let's talk about the discovery of the half-life. The discovery of half-lives in alpha and beta radiation, as you recall, is credited to Ernie Rutherford. He was one of the most influential physicists of his time. Rutherford was at the forefront of this major discovery when he worked with physicist Joseph John Thomson, also we recall as J.J. Thomson, on complementary experiments leading to the discovery of electrons. Rutherford recognized the potential of what he was observing and began researching radioactivity. 2 years later, he identified the distinction between alpha and beta rays, and this led to the discovery of half-lives when he noticed the samples of radioactive materials took the same amount of time to decay by half. Half-lives are based on probabilistic thinking. Probabilistic thinking is an idea where we expect something may happen based upon probability. If the half-life of an element is 7 days, it is most probable that half of the atoms will have decayed in that time. For a large number of atoms, we can expect half-lives to be fairly consistent. And it's important to note that radioactive decay is based on the element itself, not the quantity of it. In other situations, half-life may vary depending upon the amount of material. This is outside the scope of the elements, but for example, the half-life of a chemical someone ingests might depend upon the quantity. In biology, a half-time is the time taken for a substance to lose half its effects. Now, the most obvious instance of using half-life is with medicine. That's half the time is taken for it to have the effect to have, or for the substance to leave the body. For example, half-life of caffeine is around 6 hours. But as with most biological half-lives, numerous factors can affect that number. So let's look at half-time. Half-time is time in half. It's the time required for half of the nuclei of a radioisotope sample to decay to products. So for example, let's say we had 20 atoms of radon-222, and the half-life is 4 days. How many atoms remain at the end of 2 half-lives? Well, we start off with this formula, 20 atoms initially, 0 to 4 days, we'll end up with 10 atoms, that's half the amount. Then half that again will remain 5 atoms. So if the half-life of radon-222 is 4 days, and we go 8 days, that's 2 half-lives. So you take the number of atoms, you divide it by 2, then by 2 again, that's 2 half-lives, and we end up with 5 atoms. Let's do a quick refresh on the isotope. Remember, an isotope has more neutrons than protons of the same element. So here, if we look at carbon, we have carbon-14 on the right. Carbon-14 has 6 protons and 8 neutrons. Carbon-12 is 6 protons, 6 neutrons. So carbon-12's ratio is 1 to 1. Carbon-14's ratio is greater than 1 to 1. Now, the half-life can also be presented in a graphical format. And so here we can watch the decay of carbon-14 over time. But the half-life of carbon-14 is 5,730 years. So if we represent here on the horizontal axis the numbers 1, 2, 3, and 4, each of those numbers represents 5,730 years. And so we go from 0 to 1 half-life our decay of carbon-14 means that it's now half as much. We go another 5,700 years, it becomes half again. And by the time we get to 3 half-lives, the amount of carbon-14 has gone to well over 15,000 years, and it's now down to about 12.5% of the amount of carbon remaining. We go 4 half-lives, and that all amount of carbon will have disappeared. But we don't count the individual atoms. Very seldom will we count the atoms. It's more appropriate to calculate the amount that remains in terms of mass. The equation is simple. It's a simple algebraic formula. The number of atoms of any substance in a volume is the number of atoms equals n times the density times the volume divided by the molecular weight. Now, n is a constant called Avogadro's number, and we'll get onto that a little bit later in the semester. And it's equal to 6.022 times 10 to the 23 power of atoms divided by moles. More on this a little bit later, but we're not counting atoms, we're just looking at molecular weight. So let's take a look at a different way of calculating half-life. This is the first way it can be done, and I'm going to walk you through it slowly. Carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume you start with a mass of 2 times 10 to the negative 12 grams of carbon-14. How long is 3 half-lives? Well, 3 half-lives is going to be 3 times 5,730, or 17,190 years. So we need that piece of information. How many grams of the isotope remain at the end of 3 half-lives? Well, we start off with a mass of 2 times 10 to the negative 12. 2 times 10 to the negative 12, you'll calculate that, times a half, times a half, times a half, you end up with 2.5 times 10 to the negative 13 grams. It's going to be less. Remember, with each half-life, you have half as much of the original amount available. So we've gone through 3 half-lives here, 17,190 years. Another way is it can be calculated this way. We start off with 2 times 10 to the negative 12 grams initially, times a half, which brings it down to now 1 times 10 to the negative 12, times a half, which becomes 5 times 10 to the negative 13, times a half again, and we end up with 2.5 times 10 to the negative 13 grams remaining. Now, I know that math can get a little complicated, but we're primarily looking here for you to be able to do some simple calculations. Let's take a look at manganese 56. Manganese 56 is a beta emitter with a half-life of 2.6 hours, which means in 2.6 hours, manganese 56 will be half as much. How many half-lives did the sample go through at the end of 10.4 hours? Well, you can calculate that by taking 10.4, divide it by 2.6 hours, and you have 4 half-lives. Question B here is, what is the mass of manganese in a 1 milligram sample of the isotope at the end of 10.4 hours. Well, this is pretty easy math to do. You take 1 times 1/2, or 1 times 0.5, take that result times 0.5, that result times 0.5, and that result times 0.5, and you end up with 0.063 milligrams. You end up with a very, very, very small amount. It's gone through 4 half-lives. So where would you find the half-life of an isotope? Well, finding the half-life of an isotope can be challenging if you're not familiar with the math. Fortunately, much of that difficult work is already done for you. You can find the half-life of an isotope by using p-table. You remember p-table. We're going to click through here and get to p-table. On p-table, you can click on the top at isotopes, pick on an element. Let's look at beryllium. Find the isotope that you want to find. Click on that, and it will tell you that of the isotopes of beryllium, beryllium has a half-life of 154 days, depending upon which isotope of it you have. Pretty good. We also have a table, and I've given you the link for that as well. I'd like you to watch this video on radioactivity half-lives, and it will help you better understand how the stable and the unstable isotopes decay over time. That'll take you about 4 minutes to do. So click on that, watch that, and I've also posted that link for you in Google Classroom separately. Okay, let's review half-life. Half-life in radioactivity is the interval of time required for 1/2 of the atomic nuclei of a radioactive sample to decay that change spontaneously into other nuclear species by emitting particles and energy. And half-life is how long it takes for radioactive material to decrease by 1/2. All right. Want you to review your notes, check through the slides, watch that other video. Then when you're done, open up the assignment tab, go to quizzes, and answer each question. Remember, use the retake option to help practice and get yourself a nice score. Well, that's all I have for you today. You guys, if you have any questions, email me. We'll get back to you shortly. You guys have a great day.